right, welcome everyone to this new episode of the podcast Coffee Breakdown. I am Luca Viaretto, and today we're gonna dive into the topic, into the wonders of the microscopic world, in particular the at subatomic scale. And in order to do this, we have our guest, Giovanni Mocellin.
Hi guys.
Hello. So Giovanni obtained his master's degree at the University of Padua in Italy, and then he obtained recently, actually this year, his PhD on particle physics at the University of Aachen in Germany, and actually working in a strong collaboration with CERN laboratories. So welcome, Giovanni, and thank you very much for being here.
Yeah, thanks for the introduction, Luca. Actually, it's a pleasure for me to be here and to have this interview with you.
Yes. So actually, I think most people don't know, but we're also good friends from university studies. And right. I remember that we were taking, the famous train in Italy at 4 in the morning.
Between Bassano and Padua. Yeah.
Exactly. I totally don't miss that, but...
Yeah, not at all. No, indeed, in Aachen, I was having the apartment right next to the university so that I could walk to the university. That changed totally my life.
Yeah.
Improvements over time.
So Giovanni basically is a physicist, and the reason why I actually wanted to do this chat with him is because he works in a very secret lab. No, it's actually one of the one of the biggest lab in the world. There is CERN. There is at the border between Switzerland and France, if I'm correct. Right. And there they study particle physics. So the first question for me is just, what is a particle? Like for everyone, for a general public, for a general audience.
Right. So to answer this question, I will start from what we see in the microscopic world, right? So think about, for example, I don't know, I have a computer in front of me, right? We know that inside a computer we have components, and inside the components we have other micro components, and then we go down in the scale until we find what are called atoms, right? That from Greek means that's not possible to split, right? Yeah. But of course, that name was given in the time when they could not think of splitting an atom.
All right, and they were wrong.
They were totally wrong. But it's what happens with knowledge, right? Every time you improve, and that's why also we have CERN. We have this huge collaborations. We have physics in the end, right? We want to improve always knowledge in every type of knowledge, actually. I mean, we have vaccines for COVID just for that, right? We do research. So improving knowledge is the base. Now, we come from the atom, and we know now that we can split it. So we find electrons, we find nuclei. Inside nuclei, we have, again, particles. So we have little, I don't know, we can think of them as spheres just because we lack of imagination. So everything, the simplest thing we can do is to think of them like being spheres all together, attracted one to the other, and they stay together. So you can think of nuclei having protons, so positively charged balls, right? And then neutrons, neutron balls that do actually nothing for electric charge. But of course, they help the nucleus stay together. And then all around it, you have electrons. Right, now we have composed an atom. Fine. So we can think of everything being made of atoms, different ones with more electrons, more neutrons, more protons, blah, blah, blah. But actually is not the end of it, right? There's more to come and more that we discovered over the years. And so, I mean, are we made of only that? No. What are we made of? We're made of other particles. Actually, we are modified by other particles. And what is cool, for example, is I told you about electrons, right? Electrons have cousins, which are larger, heavier, right? And one of them is called muons. And these muons, for example, you can find them everywhere around you. I mean, there's a rain of muons coming on you, and they help us in modifying our DNA slowly and peacefully, actually.
That's a bit scary, actually.
Yeah, it is, absolutely. I mean, think of your hand, right? Your hand is like 10 decimeters square, more or less. You put it horizontally on the floor, and you have 1 muon per second passing through.
Okay.
That's a particle.
These come from the stars.
Yeah, basically, yeah, from all the stars. So all the sources in the universe, they pass through the Earth. They come, well, they start as other particles, of course, but then they come to the Earth. They start interacting with them. So
they collide with other.
Another key concept of particles is that they interact with the others, right?
Yeah.
So they don't live alone. We're all made of particles that interact. That's the key point. And they can interact in very different ways. We know of 4 ways. Now we want to find a 5th one. I don't know.
So basically, there is all zoo of different particles. That's what you are saying, basically. So also the proton and neutron, they are made of smaller particles.
They are all made of small particles. They're made of quarks. Many of you already may know about that. And again, you can think of what's next, right? What's smaller? What's the smallest piece that you can find if you divide that? We don't yet know. That's the cool thing about it, right? That's what we want to find out. So we have quarks, and then after that, what? We don't know yet. That's why we invest money, time, efforts, brain power, and so on.
Yeah, that's true. All right. So yeah, this is actually interesting, and this brings me to another question, actually, that I mean, a lot of us know about these different particles like neutrino and so on, bosons and so on. And one of the biggest discovery, of course, at CERN is the Higgs boson. I think it's just recent discovery. I think 2012 or something like that, right?
It was,
It was discovered.
Exactly.
Just, if you can explain very briefly, what's the Higgs boson basically to general public?
Right. So often it is referred as the Gauss particle, right? It's, well, you know, I'm not totally agreeing with that, but yeah, it's a particle that actually has changed the idea of what we have in particle physics. So we have yet confirmed that what we have as a model, because physics is made of models, right? That work to describe what happens to particles in this case. We have the so-called standard model that describes more or less everything that we see. And one missing piece in that was the discovery of the Higgs boson. And yeah, in 2012, it was found out. So normally, they explain to the general public the Higgs boson as the particle that gives the mass to the other particles. So one could think, right, you think that you're made of particles, and you say, I have a certain weight, right? I go to weigh my body, and I'm like 70 something kilograms, right? So you may think that that is due to the Higgs boson, because they always told you that the Higgs boson gives mass to particles. Yeah.
So it's all, if I'm fat, it's all Higgs boson's fault.
No, that's
no, it's not.
True.
It's not. Okay.
No, it's not true. So the Higgs boson gives mass to all the other particles.
Okay.
Right. So to all the tiny particles, but as I told you, the particles interact with the others. This interaction gives energy, and energy gives mass. So basically, these are the key concepts, and your body is more or less only interactions between the mass of your body is only interactions between the particles you're made of. Yeah, it's kind of weird, but that's fantastic. That's what I like.
This is also what is fascinating for me, because I do, for example, I'm a bit on the other side, but then so I do a bit more theory or modeling also, that this you basically, the standard model predicts something, you know, it's predictive in that sense that there should be a particle, and then you scientists that do experiments and so on, you look for it, and it's just let's see, let's test it. So this is fantastic, I think.
Right. Yeah. What is cool about particle physics is that well, nature has been given certain, I would say, schemes that are kind of uh, easy and symmetric, right? And so if you see like three things staying together, you wonder if there's a fourth one. If you see a fifth one, you see like maybe there's a sixth one. Let's find it out. And not really works. That's the amazing thing of it.
Yes, yes,
And
it's
it's like
incredible.
we have something that doesn't work today with the models we have. If we introduce a new particle, that fixes everything. And then maybe 20 years after, there's somebody that builds something that's discovering it. So yeah,
Yeah, yeah.
it's brilliant.
Yeah,
Absolutely.
but of course, also it's good to, I think, understand also for other people not doing science that it's a process of trials and errors, right? So it's
Right.
like
Yeah.
theory that has to be validated with experiment or disproved by experiments, right?
Yeah. We
So
do this every day, actually. I mean,
yeah,
we don't have discoveries every day, right? It would be fantastic, but unfortunately, that's
yeah, of
never
course.
the case, right? Yeah, indeed, we had to go back like 9 years to find the greatest one. So what are we doing now? We're uh, building new theories
Mhm.
that can explain more of what we see and trying to find out if they're true.
Yeah,
And every day we have groups around the world that do different studies with the data we collect, and finding that certain theories are not true or we have not discovered yet that they can be true. So
yeah,
we set a new limit. So far, we have not seen that, for example. That's more or less how we live our lives
yeah.
until
Okay.
somebody finds something. Yeah.
So before, and this is also another curiosity I have, just before you mentioned these interactions between particles. So can you explain a bit, like 4 or 5 interactions you said? So what are
Right.
those more or less?
Sure. So imagine that you have, starting from the basics, right? You have the sun, the earth, and the moon, right? And they're attracted one to the other. So they have orbits, they turn around each other, they say hello time to time. And yeah, so think about the sun, for example, now, and the earth. So to circle one around the other, you need a force that keeps them bound together in a way. Otherwise, the earth just would go away. One of the forces, so one of the interactions we have is the gravitational one,
Yeah.
right? So you have a certain mass here, a certain mass there. You have a certain distance between the two, and given these by constants, well, you find the force between of attraction between the two. Cool thing about gravity is that so far we've seen that it's only attractive, so we will never be repelled at some point. And so we can live our life safe, saying that the Earth will stay there for a while.
Yeah.
And then we have other types of interactions. For example, think about the sun, right? Again, and the Earth. So we're still surviving because we receive the sun rays, right? We're warmed by that. We're given energy that we transformed in any other way, right? So recent periods, we wanted to convert to solar power, right? Well, we want to convert also to fusion, and that's more close to your things. But so we want to get closer to the sun. But for the moment, we stay very far away, and we get what the sun sends to us, which are photons, right?
Yeah.
And that's another type of interaction. It's electromagnetic interaction. So the sun sends the photons, we receive them. So it's kind of an information that the sun sends to us, and we see it, right? And that's another type of interaction. And of the same type of interaction, electromagnetic, we have, for example, turning on light bulbs. That works that way, right? And we have what we talked about earlier, the nuclei and the electrons have different charge, right? Opposite charge, and that's attractive, so one can spin around the other, right? Then we have inside the nuclei this time, a strong force that's called like that because it's rather strong compared to the other forces that keeps the nuclei and the particles in the nuclei together, as well as what's within the particles inside the nucleus. So inside the protons, we have quarks, and the quarks are bound together through strong force. And the final one that we know of is when nuclei decide that they don't want to stay together anymore because it's not convenient for them to stay together, right? They want to split at some point, or they want to rearrange their energy level, and they do that in different ways. They can emit whatever they want, but one of the things they can emit is, for example, via weak force. This time there's strong, and there's of course weak. Via weak force, they can emit neutrinos that you were mentioning earlier, and then they convert whatever they need to convert into another particle to get this new particle and a neutrino out, right? And this characterized by the presence of neutrini. There's then this weak force.
Okay.
These are the main four we know of today, right?
So we said the gravitational, electromagnetic.
Gravitational. There's electromagnetic, there's strong, and there's weak.
Strong and weak. That are nuclear forces, basically.
Yeah, I would say so. Yes.
Okay.
We experience them every day, even if we're not aware of that. And that's the cool thing of it, right? Normally we think that what we do is kind of ruled by our actions, right? And whatever we see is happening is actually happening. But there's these tiny little, very microscopic world that we're not really controlling in any way, that does whatever it wants at whatever point it wants. And for example, everybody know of radioactivity. And for example, they suggest not to keep ventilated the cellars, right? That's because there's a presence of radon gas, and that's radioactive, and so that can emit particles that can interact with us and do some harm to us. So there's, even if we don't see many things, it's cool to know that they are there, because this saves our lives, it prevents us from doing stupid things. And yeah, it's very cool to know. And even if that's totally invisible to us, it's happening every day and keeping us together, so on.
So actually trying to zoom in a little bit into your work, so what you do, just if you can explain us a little bit, first of all, what's CERN? Some Italian people, they call it CERN, so I don't know even the correct pronunciation. But so what do you do? So it's just you do different experiments. If you can tell us about those different experiments, actually.
Right.
What's the aim?
So the origin of CERN is pretty back in the days after the Second World War. There was this new, it's a European feeling, knowing that Europe working together works better than having war. That worked for all, in all stages of social and human lives. And this includes science as well. And that's the cool thing about it. So it has been created to put together scientists of Europe. Indeed, it's called CERN, so CERN, which actually it's a French acronym. So it's a center for European Center for Nuclear Research. So first in English would come E instead of C, but in French it's Conseil Européen pour la Recherche Nucléaire. C'est ça. And so that's CERN, the name. So every language calls it a different way, right? In German, for example, where I got my PhD, it was CERN. It sounds very harsh, but yeah, it's the same thing, right? What's cool about that is that every language has its own, because it's it's a community of many people from many different places speaking different languages. Of course, we have English in common most of the times, and we try to work together, and that has worked since 1953, or well, when they signed the convention for it. And then they started to work from 1954, and we're still working today. And it started in the Swiss part, because Swiss was neutral, during the war. Swiss was neutral, so they started from that place. And then, well, Swiss has an issue. So Switzerland has pretty costly things, whatever you can think of, and also land costs a lot. So it was worth expanding towards France. Okay. That's why now it's in between Switzerland and France. Yeah. So from there, they started with a few buildings, with a few particle accelerators, okay, right? And then they expanded that, and now we have an accelerator of particles. So we give energy to particles to accelerate them. We have it in a tunnel that's like 100 meters underground, and that's 27 kilometers long. And we started with particles accelerators. They were like tabletop experiments. So a lot of technology has been developed.
What you're referring to is the LHC, if I'm correct, right?
Exactly, yeah. So our main machine there, the accelerator, is the largest that we have, is 27 kilometers long, and it's called Large Hadron Collider. So we said about particles, there are different types. There are azuo particles. One of the types is called hadrons, and hadrons are the ones that are composed of quarks, right? And we have like particles that are composed of quarks that we can accelerate. So we give them a certain energy, right? We pump energy basically through electric fields. So we have a lot of power demand. Actually, CERN consumes a lot of electrical power. And we accelerate particles, and then we collide them. So first is accelerate, and then is collide. That's why it's called large, because it's very large. Hadron, because we use hadrons. And collider, because we accelerate and then collide them. Why do we collide them? So basically we smash them. We accelerate one against the other. So we take a proton, we take another proton, actually bunches of them because it's more convenient, but you can simplify it with one and one, and you basically smash it, right? You take these two particles with very, very high energy. So for example, if you take one of the particle bunches that we have, we call it beam of particle, because it's like a train of particles. You take the energy of a beam is more or less like the energy of TGV, the train Grand Vitesse in France, at 300 kilometers per hour, full of people. So that's the energy of that system,
okay,
right?
All right.
And only of tiny particles that you don't even see, right? And then we smash them one against the other. And what do we obtain out of that? So, Einstein was formulating the law E is equal to mc squared. That's very famous. Most of the people know it, actually. But what I'd like to convey as a message is that energy is equal to mass, and mass is equal to energy. That's a totally crazy thing, that if you take particles that are made of quarks, you smash them, right? You give a lot of energy and you smash them. You can actually create particles that are not there earlier, and that are not composed of the same components of the particles that you're smashing. You take new ones. So energy is converted directly into mass of another particle. That's totally different.
That's great. That's why, for example, I heard X is quite massive, right? So that's why you need this much of energy to produce.
Yeah, indeed. So we start with we start with particles that have already a large mass. We accelerate them, and then we obtain lots of different things, right? The energy doesn't go to only a Higgs boson, but it goes also to an Higgs boson normally. And then we need to create that. So we need the energy that's required to create it out of nothing, basically. So just out of energy, right? And that's why we accelerate them, as you said. Yeah,
that's
so it's pretty
interesting.
massive. It's not as massive as we would have liked earlier
Oh,
when we theorized it, because it's quite light and it doesn't explain all that we see,
oh,
right? If it was heavier, well, on that field, research would have kind of closed in a way, but now having it so half range, let's say, it leaves many doors open to find
yeah,
many
yeah.
other things.
I
That's
guess
also the
yeah.
cool thing of it.
It's also interesting actually to think about why does X have the mass that it has, right? Just why not a different
All
number?
right.
I think it's a very
Yeah.
difficult question. I don't know, to be honest.
Yeah. I mean, that doesn't become scientific anymore, right? It becomes either
Yeah,
religious or
yeah, of course.
philosophical.
Then
It's like that. That's nature. It's impressive actually. Every time I think about it, or for my PhD, I had to go back and study again all the things that I learned, and so on. Just also to write the thesis, to not to forget anything. So in studying it again, I was fascinated once more
mhm.
by actually how nature is written, what the laws are that make everything work that smoothly and that fantastically.
Yeah, yeah, yeah,
Yeah.
yeah. Indeed, indeed.
But as an answer, why is that with that mass and not another mass? Nobody knows, I guess.
Yeah,
But
yeah. I mean,
uh, yeah,
I don't know. I don't know. It's just it's a bit also scary. Like it seems like we are a bit on the edge. This is the exact mass, you know. Otherwise, if it was a bit too massive or less massive, maybe stars would have collapsed their own.
yeah,
Just I don't know. I don't know. This is science fiction at
sure.
some point, I
Yeah,
guess.
it is. But yeah, we talked about interactions, right? For example, gravity. It has a certain relation of the force with the radius, so with the distance between the masses.
Mhm.
If it was that, so we have distance at the power of -2. If it was distance at the powers of -2 point something,
Mhm.
everything would have been different, right? So yeah, it's
Yeah,
very precise numbers, very fine-tuned numbers that make everything work precisely as wanted. Yeah,
yeah, yeah, yeah.
it's
All right, but so then we come back to these particles. You said we accelerate and so on. We produce other particles that probably they decay or they produce other products and so on. And
yeah,
just how do we detect that then? So suppose we produce a
right.
very fancy, strange particles, and we want to see them. And just how do we do that?
Yeah, yeah. So indeed, having particles smashing and producing stuff is not enough for us, right? Because we know
Yeah.
what we have. We want to know what we have produced. Otherwise, it would be pointless. I mean, fancy but pointless. So what we do is to put around the areas, which are very tiny actually, areas where we smash the particles, we
Uh-huh.
put around huge detectors or assembly of detectors, which we call experiments. Um, and we want to see which kind of particles we have produced. Now, you can think of the area where we are smashing the two beams colliding of something around, I don't know, 1 millimeter in radius or diameter and the length of 20 centimeters, more or less. So it's kind of a straw,
Mhm.
right? And all around it, the detectors that we put are normally of sizes of like 15 meters in diameter and like 20 meters in length. So we put huge things around a very small area where we collide particles. And so this experiments basically with all different detectors. Now we will say a few words about what a detector is later. So we have all these detectors and say, hey, I've seen a particle and I've seen a particle with these characteristics, with these properties, right? And then we can say, okay, this particle is what I've seen. Now I'll try to see what generated that, right?
Yeah.
And so we can reconstruct what happened during the two beams collision.
Okay. So.
Now, the cool thing about it is that normally for all the particles we're interested in, we're not seeing them directly. So we have these huge things that do not see what we want to see. We just see the children or the grandchildren of what we want to see, because normally particles, especially the very massive ones that we want to find, do not last for a long time.
Yeah, they're not
They
stable.
decay, right?
Yeah.
They're not stable, they decay, and even if they travel at the maximum speed they can, so the speed of light, they can travel just for a few maybe millimeters or maybe micrometers, and so we can see whatever comes after them as a product of their decay.
Yeah. So basically, when we always say, yeah, we found X, so you basically don't see really X, but you see the products.
Yeah, we've never seen a Higgs
All right.
directly. That's almost impossible.
Makes sense.
And so what we want to do with our experiments is to see everything that has been produced, right? So that we can know that we don't miss anything, and we can reconstruct back from the children, basically going back in the tree of products and parents back to the Higgs boson, for example, right? And then we can know the properties of that, so on.
This is also reminds me a lot now reminiscence of all the statistical physics, because I mean, if you detect the products, how do you know that these are not rare events, right? And instead, it's really the event that is.
Well, yeah. So statistics counts a lot there. We never claim a discovery if we're not sure at 99.99995%. So it's what we call 5 sigmas, right? For claiming a discovery. That's very important, because if we see, for example, one event that resembles what we think it's a Higgs, we cannot say we have found it. Not at all. We need thousands of events like that, knowing that those events cannot be classified, for example, as background, so given by other processes that may give the same signature. So yeah, statistics is very important. Absolutely.
All right. So I also think you have to detect these products very precisely. So how?
Absolutely.
So there are different detectors. I think you know, it's very common. You can read in every newspaper and so on about CMS, about Atlas, and so on. What are differences about those?
So,
and if you can tell us a bit more. I think you worked on one of them, right?
Yeah. I'm currently working for one of them that's called CMS. It's compact muon solenoid, and it's like the second biggest experiment, I would say, in dimensions. Actually, we have in total 4 main experiments at the LHC. We have 2 which are called main purpose, so they can detect basically everything or kind of everything, and they're huge. And one is Atlas, and the other one is CMS, the one I work for.
Okay.
And the other 2 are more, let's say, dedicated to certain purpose in discovering a certain sector of particle physics. And one is called a LHC-B, for beauty particle, so the beauty quark. That's what at the beginning they were focusing on that, and now they're doing many other things, but normally they work with quarks, and they're rather small, and yeah, they have a very peculiar geometry. I will tell you more about that later. Then the 4th one is only dedicated, or mostly dedicated, to collisions where we don't have protons anymore, but we have lead nuclei, which are very huge, stable nuclei. They have, instead of one or a few, actually a few protons and neutrons, we have in total 208. So it's pretty big nuclei smashed together, and when we smash them, it's generating the so-called quark gluon plasma, which is a state of matter that actually it's thought to be the one after the universe was generated after Big Bang, if we ever had a Big Bang. But yeah, when matter was very compressed, we had the so-called quark gluon plasma that then inflated, and we have the universe we see today. And they're trying to study how matter interacts, so how quarks are interacting with each other through gluons and so on.
That's to
and that's
study
very,
the,
very
the early phase of the universe, right?
exactly. Yeah.
Okay.
Yeah.
Okay.
So in the other three experiments that we study actually particles only.
Okay.
The principles are more or less the same. Also with quark gluon plasma, we study the particles that come out from there, and we study all the properties of that to reconstruct what's happening there. So again, you never see directly what you want to study, but you see all the stuff that's spat out, right? Yeah, so we have now talking about more about my experiment, so my own experience that I had, that's more or less identical to Atlas. We have in CMS a huge detector, so a huge assembly of different parts that work together as a single detector. And what we want to do basically is to track all the particles that come out of a collision, right? So we have particles that go all the ways around, and we have even multiple collisions when two being crossed. And so we want to precisely reconstruct all the particles that pass through our detector to then say, hey, this particle comes from that point, and that particles come also from that point. Maybe they've been generated by the same one after a decay, right? That's why we need to be very precise, just to have a clear idea where they come from, to say, hey, the parent of them is the same and has these characteristics.
Yeah, so that is what you were working on, basically.
Yeah, and more in specific, so these huge things are composed of many different parts. I was working on one of them.
Yeah.
And it's one that has rather new technology compared to the others, because CMS is there basically since the early 2000s, right?
Yeah, so you
They
need an
started
upgrade.
collecting. Right. So yeah, after a while, things start to be old-fashioned. So we want to be better and better over time. So we want to upgrade what we have there and add new things with new technologies to improve the detection. And yeah, what I was working on was one of these pieces that can see the particles that traverse them, right? So again, particles come to the detectors. They normally have a sensitive part, or what we call sensitive part. It can be whatever material. It's normally other silicon, so kind of chips that we have. And then it can be gas, it can be crystals, and they undergo all different processes to see when a particle is interacting with them. I was working on gas detectors. So we have a gas volume that's filled with normally argon, CO2, and sometimes other gases. And when a particle is traversing them, in the gas, we have the generation of ions and electrons that are split. So for a fraction of time, you have an ionized atom. And of course, if you leave it there without doing anything, then they recombine. So you cannot do much with that. But we apply electric fields. We collect the electrons and the ions. And we see then that, well, some electrons are coming in this region of our detector at this point in time. So something has happened there, right? So we see what we call a signal. Then out of a signal, we have some processing, and we can say, hey, something has passed through there. And something has passed through there as well. And yeah, so we see particles that way.
Okay, that's really interesting. Also, so then you said you did this upgrade and so on. So my question is that, from ignorant in this perspective, because I'm not working in this field, right? So just so what's next? Because I mean, I'm stuck at X boson discovery. So what did you guys do, right? After
Right,
2012?
yeah. I mean, we have like 20,000 people working for CERN,
Okay.
so they have to be doing something, right?
Yeah.
And we are indeed working a lot. So actually, what's happening now is we are not having collisions. At least this year and the past few years, we had no collisions. So LHC was basically stopped for a while, and we're improving our detectors and our accelerators. And then from next year onwards, we're having collisions again. Okay. Then for a few years, we will collect data, any type of data, whatever we would like to study. Then we have a lot of people from all around the world that take this data and analyze it and tries to find out something, right? And then again, we will have a stop of LHC. It will happen probably in 4 or 5 years. And for a few years again, we will improve more because technology, you know,
improve.
like
Improve.
even
What do you mean? So in which aspects?
right. So you know, even on mobile phones, like 10 years ago, we didn't have what we have now. So we have many more possibilities in capability of calculation, for example, that we didn't have earlier. We have new electronics. We have also new new detectors invented, and we want to implement that. So what we want to do is being always more precise in tracking particles, so seeing where they hit and at what time they do that, because we have a zillion of particles smashed every 25 nanoseconds, so it's very small interval, and then after 25 nanoseconds we have another bunch of particles smashing again. We don't want to confuse this particle with that particle, or that you know can, of course, they all can be confused in time. They can all be confused in space. They can all be confused in whatever type. So we want to be as precise as we can. That's why we're investing a lot of money, time, and effort to have better, more precise detectors.
Yeah, that's it. Yeah. I think it's useful also to put some constraint of the theories, right? If you can measure something very precisely, it's also useful for theoretician to say, we know this value with this accuracy, right? So how about
right? Absolutely. And it may sound weird, but we can use that in two ways. So one thing is to confirm that a value is as we expect, right? So for example, we say this value has to be 2, and we measure it as 2.0000001 plus minus whatever error, right? If that error is huge, you cannot say anything. I mean, the number is closed. If you see like 2 or 2 plus 1 or whatever, that doesn't really make sense, right? If you have 2 plus minus 1, is that compatible with 2 that you expect? Of course, but do you have a deviation? You don't know. So you have to study more to have more statistics. That's why we want to run for a longer time and take more data to be precise in that and say, okay, the theory maybe, or so far we know it's accurate. So we confirm that is accurate. But also there's, you know, the flip side of that. If we measure more precisely and we know that we have measured this quantity like with never seen accuracy, and that is close to the number that we wanted, but actually is a tiny bit far away. If you're precise in that measurement, very precise in that measurement, and it's a little bit off, then you can say there might be something beyond that.
Yeah.
Right?
I agree. All right.
And that's how we're using it.
Then I have really $1 million question, because I think for most of the people, it's really difficult to grasp this. Why do you need this, right? So why do you have to spend so much money, right, on these very precise measurements, or finding something that we cannot even see them? You know, all these particles, you're telling me that they exist, but I don't see it in my life, right? So
right.
Why do you have, why is it important, you know, to do this kind of fundamental research?
Right. So there, I would say two main aspects of that. One is, or maybe three. Let's say three. Uh, First one is it's the very basic answer is it's very useful as it was created. CERN was created to have scientists used to work together in that type of way. It's an amazing environment, really. So being used not to fight against each other, but to collaborate is already a great target that we are achieving every day. Of course, giving millions or more, often it's more, only for that is not worth, right? So we have research on top of that. And research, any type of research is useful. And what we do at CERN for what it is, so finding new particles, you say you don't see them every day. You actually cannot see with your eyes, but you experience them every day. So they interact with you every day. So the technology you have all around you is based on that type of research, right? So finding new particles, finding new ways of particles interacting with each other changes our lives or has changed them, right? For example, I don't know, well, we always mention hydrotherapy for cancer, right? So it's a new way of curing cancer using accelerated beams
That's
that
another
are
line of
shot.
research at CERN, right?
That's another line. That's a parallel one, but everything that we can do in being more precise in accelerating the beams and making them collide reflects to that type of research, right?
Yeah.
And so we improve as human beings also to handle our own tools that we invented, but we need to be more precise in that to be more effective. And of course, you can use then whatever you find for any type of application. Then
Yeah.
it can be medicine, it can be technology, it can be whatever. For example, you all experience that at some point your computers can fail, right? And I was mentioning muons earlier. Uh, Muons can interact with your computers and mess up the memory. That happens. That
And
normally
neurons,
happens.
they
Muons can
mess
do
up the
everything,
DNA,
right?
they mess up the
Yeah,
computers.
of course. But evolution is due to particles interacting with our DNA. Otherwise, we would be primordial beings and staying the same way. Modifications are normally good, and
Yeah.
improvements are
I
good.
think no, it's good also to say that even though it's fundamental research, research for the sake of knowledge, right? Still, it has
Yeah,
application, as you
it's
said, right?
sure,
For
sure.
example,
It
the
has.
magnets that you need in LHC probably can have application also on different technological
Yeah,
application, on different
yeah.
lines of research or in
One
industries and so on.
Right.
So it's,
One of the main outcomes of, well, all types of research normally of like fundamental research is the technology transfer from that. So
yeah,
we, of course, push the limits of our technology to have the best in our field. And then we take that and we use it for real, let's say, everyday life applications. And that's what the coolest thing is. Um, then, of course, there's also let's say, a third reason why we do that, which is uh, it's best to know what you have around you, right? Than not knowing anything, because it can save you from anything that happens, right? I was
yeah.
mentioning sellers earlier. If you know what's happening around you, then you can take actions,
Yeah,
right?
I would like to conclude a little bit of this conversation, actually talking a bit about more the human side. So I was working at CERN, interacting, you said there are different peoples from different nationalities and so on. So how's the environment there? Really from the human point of view, it's just like open, like university campus, or is a bit more secret lab? I don't
Yeah,
know.
yeah. I mean, it's not a secret lab. I would not call it that way, but it's a safe lab. So we have a safety measure
Yeah, of
because
course.
we don't want anybody to get in. Uh, for many reasons. One of them is that not every part of the buildings is safe for exposing humans to, for example, radioactive sources or beams. You would never want to be into LHC when it's turned on. I mean, you would never survive that. So, we have restrictions, of course, but it's not secret. I mean, it's best if it is advertised, actually, because advertisements always brings knowledge and peace to people, because most of the times you hear people saying, hey, you're doing something weird at CERN, right? You're making particles explode and we will explode all together. No, it's not true. I mean, it's very safe. So everybody has to know what's happening inside, even in a very simplified way, but it's good to know. So we don't want to be a secret lab. We want to show what we do. We're proud of what we do. But of course, you need restrictions. And so it's kind of a cool thing that you get in and you have your badge. You're allowed only to get in if you have your badge. In certain areas, you need a dosimeter that measures the radiation that your body would absorb to be safe for you, of course. So you would be warned if there's something going wrong. And so you kind of feel special in a way when you get in, but everybody can feel special. That's the cool thing of it. We have also lots of visitors that we can bring in and so on. So it's a nice place. It's a good environment to be in because, well, like I said, everybody can feel special inside there, and everybody has its own characteristics, its own, let's say, culture, because we come from different nationalities. Actually, we have like 110 different nationalities in CERN. So it's a very rich environment. It's not like a university because there's no real like lectures or teaching for the entire year. It's mostly research. We have also seminars and so on, but it's mostly research. And people there are often feeling, at least this is what I always felt, that CERN is kind of your second home. And it's one of the best feelings you can have. Yeah, because nobody judges the others. We all know that we are all different, and we don't have only physicists there. We have all types of different experts and not experts, because, well, it's kind of a city, actually, since we have thousands of people every day being in there, eating in there, sometimes sleeping, or not sleeping because we want to continue to do research overnight. That also happens. So there's people always around you, and people with the same, passion that you have, with the same will that you have to find something new, and you kind of feel that you're within a family, a very large one, with different people, but that's always like families are, right?
So you would definitely recommend working there, basically.
Yeah, absolutely. Or at least have an experience there.
So do you need to be like a physicist only, or if you study, I don't know, computer science, informatics, or whatever other field, you can work there? How does it?
So mostly everything is needed. Like we start from, we think that we are all physicists, but that's not true, because I tend to say that physicists are good in doing everything, but not enough for doing something. So we're very non-specifically trained, and so we need people that is very trained for certain tasks. For example, we need a lot of engineers, because as physicists, we're not able to put together something that does not require tape. We're not good in building stuff. We need a lot of people that know what they're doing in designing and putting parts together. So engineers is one of the main figures that we have there. I think we have even more engineers than physicists working in CERN, actually.
Makes sense.
And then, of course, we need IT, and because we have lots of data to handle, because with these detectors, we collect like a megabyte every 25 nanoseconds per detector. So, memory fills up quickly. And then we have to handle all that. We have to share it with the rest of the world, where we have all the universities collaborating and having groups that want to access the data and analyze it. So we want also to have, safety in terms of computing. So there's lots of IT people that work there, taking care of all this, and also giving a lot of resources that we need all the day long. We have computer farms and servers and so on. For
Yeah,
example,
yeah.
I think
Also,
that,
sorry,
yeah.
finish.
Yeah, so I think that we need mostly one single computer with one monitor, and we can do whatever we want as physicists, just because we connect to all the IT infrastructure from
Yeah, yeah.
wherever in the world, and we can see and continue our research. That's the amazing thing of it. And of course, we need all these figures inside CERN. Also, we need to eat. I mean, there's a lot of different things that we don't see like advertised normally, because when you have a discovery, it's like physics, fine. But then, well, we need administration. There's lots of people in administration,
Yeah, of course,
because it's a city, right? So you need all the different parts. We have safety. We have, yeah, fire brigade. That's what they train me for, to
One
call the
thing,
fire brigade.
one thing I really admire about this world, let's say, also with respect also to other fields of physics or science in general, is that it's the communication part. I think
Yep.
that CERN is taken really seriously, in my opinion. So what do you think about that? Because sometimes, you see a lot of people seeing this in a bit, I don't know, it's a bit, it's a bit a strange way, right? So I don't know, like fake news and so on. It's
Yep.
like at CERN you're producing black holes that they will,
Right.
I don't know. Or we had a minister like few years ago that says that they build a tunnel, that
Yeah.
to let the neutrinos pass. This kind of
Yeah.
news, right? So what do
Right.
you think about communication at CERN? Now is it handled and so on? Can you do better?
Well, you can always do better, but no, it's a great effort that we have to communicate to the other people, as this is in simple words also. But that's very important to tell the others what we're doing. And if when you know what's going on, you're not scared anymore, right? And you shift this from being scared to being fascinated, and that's what we want to convey as a message. What we do is fascinating. It's not scary. It's not dangerous. We have all the precautions for that not being dangerous, right? Um, and so communication at CERN happens well within CERN is very important. There's often, all the means of communication that we have. For example, now I'm connected through Zoom, right? And my Zoom account is hosted at CERN. So we have this type of platforms that we can use to communicate among our groups, also to communicate with others on the other side of the world, but
Yeah,
also we have platforms to communicate to the outside world from CERN, let's say, to the people. I would say that we're doing good. Of course, we can do better. We could simplify things more and have it shared with the others. Then, of course, maybe new in the news that would not be very appealing, but it would be nice. And I like when I see, for example, in the summer we had new. It's not really a discovery yet, but we had new data on how muons behave in terms of the gyroscopic momentum. But whatever, doesn't matter that. What matters actually is how it was well advertised. It was not done at CERN actually, but it's how science and particle physics in general advertises what we do. So, for example, in the Italian television, I saw there were lots of public debates, having experts interviewed and so on. That's very useful, because then people can know, first of all, where all the money go, because we said we spend a lot of money in doing things, but it can be it is useful for everybody to know that. So that I would also promote more if possible.
Yeah. Okay. Thanks, Giovanni, for being here. Thank you very much. And well, we stay in touch. All right.
Yeah, of course. Thanks a lot, all of you. Bye.
Bye.